Hey folks, how's it going? It's Mr. Murray coming to you with a due now for Course 1 Honors for Friday, May 22nd, 2020. Welcome to the end of Week 9. You've made it, and I'm so excited to be having our hangout today. In this little due now, I'm going to be talking about exponential growth and decay. It'll be your job to figure out which one it is and how to set it up. I would recommend you go back and take a look at the exponential modeling activities and kind of resources that we did earlier this week if none of this is making sense to you. And there's also an example from the Do Now video yesterday. So here's the situation. Your car was $20,000 when you purchased it. That's what it was valued at. Each year, it depreciates by 20%. 3 years after you take your loan, you still owe about $12,000. How much more or less than your car is currently worth is the value of your loan. So what it means is this. When you roll your car off the lot, you just buy it, you get a loan so you can pay for it because you don't have $20,000 on you. At that initial point, the value is $20,000. Each year, it depreciates. Depreciates meaning lose value by 20%. So it loses value by 20%. And then 3 years after you take your car loan, you still owe $12,000. So what I want you to do, pause the video, figure out how much more or less is your car worth currently than your $12,000 loan is worth. And I recommend, by the way, that you use a scientific calculator, such as this one on Desmos. See this link down here. All right, and then when you're ready, unpause, and you can see what I got. Okay. So what we're looking at is an exponential model. Now, this is a decay model. So in general, remember, an exponential function follows the form of a times b to the x. When we have an exponential decay, it follows the formula f of x equals a times 1 minus r to the power of x. Now, remember that what this means is a is the initial value you're starting at, right, when x is 0. And if you think about it, when x is 0, 1 minus r to the power of 0 is 1. So 1 times 20,000 is 20,000. So that makes sense. And now rate is the rate of decrease. Because if you think about it, if it loses 20%, then at the beginning of each year, it had the 100% that it started with from before minus 20% of that. So if it started at $1,000, I'm going to say 10,000 because that's a little bit closer. The next year, it would have that 100% minus 20% of that $10,000. So I'd have 10,000 minus 2,000 or 8,000. Then the next year, so I'd start at 8,000 and I'd go 8,000 minus, so I'd have that 100%, and then I would take away 20% of that. Okay, and when I do that, it's 8,000 minus 1,600. And that's 6,400. So you can see you've actually gone down by less. Now you've only gone down by 1,600 instead of by 2,000. So you've gone down by less, but you've still gone down by quite a lot. Now this is only for 10,000. But the idea is if you start at 100% and you take away 20%, then every year you have 80% of what you had the previous year. Think about it as a sale. If you go out and you got a pair of jeans Okay, pair of jeans, and there's a tag on the jeans, and it says 40% off. Okay, well, if you start at 100% of the jeans and you take away 40% of the jeans, then what remains is 60% of the jeans. So next time you go out shopping on your phone, what you do is you take the price. So let's say the jeans cost, I don't know, $89.99, pretty expensive jeans. You just take, if you want to know, instead of doing all that math, you just take 60%, the remaining amount that is left, because you removed 40%, and you multiply it by the cost of the jeans, and that takes you right to the cost that you're going to have to pay. Okay, so based on that principle, this is the function that we want. Now, 3 years after we take the loan, x equals 3. So on my scientific calculator, because remember, this is not stuff we do in our head. It's just based on the numbers. We're not going to do that. Okay, that's not what I'm evaluating right now. I want to see you set up the model. Okay, if your calculator does the rest of it at this point, that's fine. To the power of 3. Now, notice that it's 0.8, and 0.8 is 4/5. 4/5 is between 0 and 1, so we expect it to be getting closer to the asymptote as time goes on. And so we expect the values to be decreasing in this case. And oh, there we go. So we get $10,240 as our final answer. $10,240. And so what that means is that the loan is worth, well, let's do the math. So now let's clear it out. So we want to know how much more is the loan than the car, or how much less is the car than the loan. So let's do 20,000. Let's do rather. So the loan is worth 12,000, and then the car is currently worth 10,240. I always hit enter. I don't know why. So $1,760. So what this means is that the loan, what's left on the loan, is worth $1,760 more than what the car is worth. So what that means is if you were to sell your car today for what it was worth, you would not be able to pay off your loan because you'd be $1,760 short, because the car is worth that much less than what the loan is worth. Now, this is a pretty common occurrence, and that is because cars in general, from an investment standpoint, are not very good investments. They typically lose value very quickly, and relative to how fast you're paying off the loan. Because if you think about it, right, a typical car loan, your first car loan is likely to be 7 years long. So you're likely to be paying off, more or less a fixed percent each year. Although what you pay it off, right? You get less interest as time goes on. But if you imagine you're paying off, 1/7 of it each year, well, your car is losing value a lot faster than that. Okay, so this is just another little exponential modeling application. Hopefully you're able to get this right. If so, congratulations. If not, try to figure out where you might have gone wrong. Today we're going to make sure we take a look at whatever's on the Google Doc and follow it from there. Make sure you're keeping up with everything that we're doing. Best of luck. Don't forget to love math, and have a wonderful day.